March 15, 1944. Pratt Army Airfield, Kansas. A bomber worth more than $500,000 sits on the runway, its right engine belching fire. Flames roar from the metal housing, melting through the wing as mechanics sprint across the tarmac with extinguishers that barely matter. Within minutes, the B-29 Superfortress, America's most advanced weapon, is a heap of twisted metal and ash. But this isn't a combat loss. There are no enemy fighters overhead. No flak. No mission gone wrong. This is Kansas. A training flight. It's the fourth bomber to burn this week. Across the state, more are going up in flames. Some explode before takeoff. Others melt into the runway. And with every fire, the Army Air Forces are watching their billion-dollar dream turn into a nightmare. The B-29 was supposed to be untouchable, the aircraft that would end the war. Instead, it's killing its own crews before ever leaving American soil. What no one knows yet is that the answer to this crisis won't come from engineers in white coats or generals barking orders. It'll come from a 38-year-old plumber from Cleveland, a man with no engineering degree, no military background, and no reason to believe he could change history. His name was Tony Valiter, and his idea was so simple, so obvious, that every expert in the country had missed it. The B-29 wasn't just another airplane. It was America's most expensive wartime project, bigger than the Manhattan Project when you count the factories, the tooling, the logistics, the crews training around the clock. The Superfortress promised altitude, speed, range, and the power to reach the Japanese mainland. On paper, unstoppable. On the runway, it was a different story. Engines ran hot, then hotter, then they lit off like torches. Of the first 175 B-29s delivered, 16 burned to the ground. 47 more suffered major engine fires. That's a failure rate you don't quote to your crews unless you have to. Ground schools drilled evacuations until they were muscle memory. Unstrap, out the hatch, hit the tarmac in 45 seconds or less. This wasn't a fluke at one base. It was systemic. Smoky Hill, Walker, Great Bend. One bomber exploded during takeoff and never cleared the field. Another melted a wing spar in minutes. The fire bottles designed to flood the cowling couldn't even reach the blaze. The flames started deep in the engine, behind baffles, trapped where the extinguishers couldn't bite. The clock at headquarters kept ticking. General Hap, Arnold had promised President Roosevelt that B-29s would hit Japan by June 1944. Missed that window, and the most ambitious air campaign of the war stalled before it began. Every lost airplane meant months of work and 11 lives on the line. Confidence cracked. Crews started calling the Superfortress the flying funeral. Some even asked to transfer to older, slower bombers because at least those didn't burn over friendly farmland. Engineers threw fixes at the problem. Bigger inlets, new cowl flaps, larger oil coolers. Marginal gains. No cure. The rear cylinders kept cooking. The R-3350's power came with a price. Heat the system couldn't shed. And with every test flight that ended in smoke, the schedule slipped closer to impossible. Money couldn't solve it. Degrees couldn't solve it. Time was running out, and the most advanced bomber on Earth was losing to physics. Cleveland, Ohio, 1930s. A man crouches in a basement with frozen hands, trying to make a water line cooperate with century-old pipes. His name is Antonio Tony Valiter, and he's not thinking about airplanes or war. He's thinking about pressure, flow, and how water always finds the path of least resistance. Tony left school after 7th grade. His father ran a small plumbing business, fixing leaky radiators and ancient boilers. Tony grew up crawling through crawl spaces, solving problems with a wrench and instinct. He didn't study fluid dynamics, he lived it. He learned that you can't fight flow, you have to guide it. By 1941, the world was at war. Tony was 35, too old to fight, too young to sit it out. So when he heard that aircraft factories were desperate for mechanics, he signed up. He thought maybe pipes and engines weren't all that different. He was right. The Army Air Forces sent him to Pratt Army Airfield in Kansas, a major training base for B-29 crews. Tony spent his nights under the wings of bombers, drenched in oil and sweat, maintaining the most advanced engines ever built. Engines that terrified the men who flew them. While the engineers chased equations, Tony watched how the air flowed through those engines like water through a pipe system. He noticed where it pooled, where it slowed, where it boiled. And one night, when yet another overheating engine came into the hangar, Tony saw something that no one else had seen. He saw a clog. It was late September 1944, and the hangar was quiet except for the ticking of cooling metal. Tony was assigned to inspect a B-29 engine that had nearly caught fire during a training flight. The pilot shut it down just in time, and now Tony had to find out why it overheated. He removed the panels, leaned into the cowling, and stared at the back of the engine, 18 cylinders arranged in 2 tight rows. The front ones gleamed silver, catching the breeze from the hangar doors. The back ones were scorched black, heat-warped, almost charred. To Tony, it didn't look like an engine. It looked like a water system that couldn't breathe. The cooling air came in fast, hit the front cylinders, then stopped. There was no real exit path for that air to move through the rear. It sat there, trapped and heating up, the same way a radiator on the top floor of a house stays cold because the pressure can't reach it. Tony ran his hand along the aluminum baffles, thin metal sheets that were supposed to guide airflow, and instantly knew what was wrong. The engineers had tried to force the air where it didn't want to go. They built walls, baffles, and vents, but none of it created a natural path. The hot air just stagnated and baked the rear cylinders alive. And that's when Tony had the thought that changed everything. "What if," he muttered, "I just reroute it?" He grabbed his notebook and sketched an idea, a series of small aluminum ducts that would carry fresh air directly to the rear cylinders. Simple pipes, shaped to bypass the blockages and deliver airflow where it was needed most. No redesign, no million-dollar re-engineering, just plumbing logic applied to aviation. It was a ridiculous idea. At least, that's what anyone trained in aerodynamics would say. But Tony had spent 2 decades fixing problems that shouldn't exist on paper. He didn't trust theory. He trusted flow. For 3 nights, he stayed after hours, scavenging parts from scrapped bombers and cutting aluminum tubing by hand. He bent and shaped the ducts himself, fitting them snugly between the cylinders. When he was done, the modification looked crude, like something cobbled together in a garage. But it was neat, functional, and made perfect sense to a plumber. Tony didn't tell a soul. No paperwork, no approvals. He just noted, "Cooling system inspection complete. Engine cleared for test." The next morning, a test pilot rolled the aircraft out to the field. The engines roared to life, and the temperature gauges began to climb, except this time, one of them didn't. The right inboard engine, the one Tony had modified, ran 60 degrees cooler than the rest. The pilot assumed the gauge was broken. Tony knew better. When the temperature logs came in the next morning, the numbers didn't make sense. Rear cylinder temperatures that usually spiked past 500 degrees were holding steady around 420. The crew assumed the sensors had malfunctioned. But when they pulled the cowling to inspect the wiring, they found something no one could explain: hand-bent aluminum tubes running through the engine like plumbing pipes. The engineering officer lost it. Who did this? Who authorized a field modification to a $35,000 engine? Every head turned toward Tony. He didn't try to deny it. They pulled him off the line immediately. He was marched into the office of Major Donald Peterson, head of aircraft maintenance. The major's voice was flat. "You understand this could be a court-martial, right? Unauthorized modification to government property, endangering aircrew." Tony nodded. "Yes, sir. But it worked." Peterson looked up. "What do you mean it worked?" Rear cylinders ran 60 degrees cooler. No heat stress. No smoke. The room went silent. Tony explained it the only way he knew how. Not in aerodynamic jargon, but in plumbing terms. "Sir, air's like water. It won't go where it's blocked. You've got to give it a path." Peterson flipped through the data again. The readings were impossible. The standard engine barely lasted a few minutes at high power before temperatures redlined. Tony's test held steady the entire run. He should have dismissed it, should have written Tony up, grounded him, buried the report. But something about the mechanic's calm certainty stuck. Peterson picked up the phone and called Wright Field in Dayton, Ohio, the headquarters for the Army Air Force's Engineering Division. "You're going to want to see this," he said. 2 days later, Tony was on a transport plane to Ohio, carrying his handmade ducts in a canvas bag. A plumber's toolkit about to face the most intimidating engineering board in the country. Wright Field, Dayton, Ohio. Tony walked into a conference room filled with men in uniforms and lab coats, colonels, engineers, and officials from Boeing, Wright Aeronautical, and the National Advisory Committee for Aeronautics. On the table sat a disassembled engine model and Tony's crude aluminum ducts, laid out like evidence in a trial. The engineers looked at him like he didn't belong there. To them, he He was just a mechanic who'd gotten lucky. A plumber with a wrench pretending to solve a problem that their best minds had been tackling for nearly 2 years. Dr. Harrison Evans from Wright Aeronautical started the meeting, his tone clinical. "Sergeant Valader, your temperature data is interesting, but we have significant concerns about your modification. These ducts reduce total airflow by nearly 8%. That's unacceptable in a high-performance engine." Tony didn't flinch. "Maybe. But the air that does flow goes where it's needed. The rear cylinders stay cool." Another engineer jumped in, shaking his head. "You've created turbulence. You've violated the basic principles of aerodynamic flow. Your system shouldn't work." Tony shrugged. "Then maybe the principles are wrong." The room erupted with murmurs. One man snorted under his breath. Another flipped through Tony's sketches like they were a joke. "Even if these numbers were accurate, this design is impossible to mass produce. It's hand-cut aluminum. You expect us to retool an entire factory for this?" Tony kept his voice steady. "They're just ducts. Any shop can make them. Without stress testing? Without vibration data? We can't risk crews' lives on backroom mechanics." That's when the door opened, and the energy in the room shifted. Colonel Curtis LeMay, the man overseeing the entire B-29 campaign in the Pacific, walked in. Known for his impatience and steel nerves, LeMay didn't have time for bureaucracy. He glanced at the charts, then at Tony. "Sergeant, I've got bombers burning up on the ground in Saipan. You telling me you can fix it with some tubes?" "Yes, sir," Tony said simply. LeMay turned to the engineers. "You've been at this for 20 months. What have you got?" One of them hesitated. "Incremental improvements, sir." "Has it worked?" LeMay cut him off. Silence. He picked up Tony's data sheets and tapped them on the table. "This man did in one night what you couldn't do in nearly 2 years. You're going to test his system properly. Stress it, shake it, tear it apart, and if it works, you're going to put it into production. 20 days. Not 20 weeks. Not 20 months. The engineers protested. "That's impossible." LeMay leaned forward, eyes cold. "Then work faster. Because in a month, I'm sending 500 B-29s to bomb Japan, and I need engines that don't kill their own crews." He turned to Tony. "Sergeant, you'll stay here as a consultant. Help them build it right. And don't let them overcomplicate it." Then he paused at the door and added one line that Tony would never forget. "Sometimes the best solution is the simple one." October 15th, 1944, Wright Field Testing Facility. Rows of engineers and officers gathered around a roaring engine anchored to the test stand. It was Tony's modified R-3350, rebuilt with precision replicas of his crude aluminum ducts. Every sensor was wired, every gauge ready to record. The plan was simple: push it until it breaks. The baseline test came first. A standard R-3350, untouched, unmodified. Within minutes, the rear cylinder temperatures climbed past 560 degrees Fahrenheit. At 70 minutes, the exhaust valves failed. Metal cracked, smoke poured out, and the engine died exactly as expected. Then they fired up Tony's version. At full throttle, the sound was deafening, a wall of noise that shook the ground. Everyone expected the rear cylinders to start glowing red within minutes. But the gauges barely moved. 410, 430, 445. The rear cylinders were running cooler than the front ones. 2 hours in, still no heat damage. 3 hours, still steady. The engineers looked at each other, stunned. The test was supposed to find the breaking point, but it never came. Dr. Evans checked the readings 3 times. "This can't be right," he muttered. "We're moving less air, yet cooling more efficiently." Tony just grinned. "It's not about how much air you push through," he said. "It's about where it goes." That one line changed the way they thought about cooling forever. Within days, Boeing engineers refined the design, giving it a name: the Valader Bypass Cooling System. On the factory floor, crews started calling them Tony ducts. Production lines retooled overnight, the new ducts becoming standard on every B-29 rolling out of Wichita. By November 1944, the first modified bombers reached the Pacific. Flight tests confirmed what the lab already knew: the fires were gone. Engine temperatures stayed stable, even on 9-hour missions. Crews who once feared their own aircraft began to trust them again. Before the modification, the Army Air Forces lost over 20 B-29s a month to engine failures. After it, fewer than 4. Engine fires dropped by more than 80%. Tony's plumber's fix had saved the entire program and thousands of lives. By the spring of 1945, the skies over Japan were filled with B-29s that no longer burned themselves alive. The bombers that once terrified their own crews were now flying 9-hour missions without a single engine failure. The transformation was so dramatic that Japanese intelligence assumed the Americans had secretly built a new generation of aircraft. They hadn't. They'd simply installed Tony Valiter's ducks. The war ended within months. The same bombers Tony helped keep airborne carried the atomic missions that closed it. In the official reports, the success of the B-29 program was credited to industrial efficiency, strategic planning, and engineering excellence. Tony's name appeared nowhere. When the Army called him to headquarters to pin a medal on his chest, he refused it. "I didn't do anything special," he said. "I just fixed a cooling problem." He went home to Cleveland, traded his mechanic's overalls for a plumber's belt, and never spoke about the war again. To his neighbors, he was the man who came to fix leaky faucets, not the man who saved 2,000 airmen. In 1947, a local reporter discovered the story and tried to interview him. Tony turned it down. "Give the credit to the pilots," he said. "They're the ones who risked everything." The article ran on page 7, a small piece about a humble plumber who solved a billion-dollar problem. Few noticed, but his idea didn't die with the headlines. The Valiter bypass system became the quiet foundation of modern engine cooling. Decades later, engineers renamed it directed cooling, building it into everything from commercial jets to fighter planes. The same principle that Tony had shaped by hand in a Kansas hangar now powers spacecraft and high-performance engines around the world. Tony never knew. He died in 1982, still working as a plumber. His obituary mentioned that he'd served in World War II, nothing more. At his funeral, a single man in uniform stood silently in the back. Afterward, he approached Tony's son and said, "I flew B-29s in the Pacific. My crew made it home because of your father's work." Tony's son looked puzzled. "My father never said anything about that." The veteran smiled. "That sounds like him. The kind of man who'd save lives and never think it was a big deal." Tony Valiter's story isn't about luck or genius. It's about seeing differently, about the kind of insight that comes from experience, not education. While engineers chased equations and airflow diagrams, Tony looked at a $1 million engine and saw a plumbing problem. He didn't overthink it. He just built a better path for flow. That simple act, bending a few pieces of aluminum tubing, saved thousands of lives, kept the B-29s flying, and helped end a world war. And yet, when the medals came, he turned them down. He never saw himself as a hero. He just did his job. Decades later, the world runs on Tony's way of thinking. Every aircraft, every jet engine, every spacecraft uses some form of his principle: directed cooling, bypass flow, guided pressure. His idea lives in every skyborne machine built since. But his name doesn't. History forgot Tony Valiter. But maybe that's what made him different. He didn't fix the world to be remembered. He fixed it because it needed fixing. Sometimes, the greatest innovations don't come from laboratories or boardrooms. They come from the hands of people who know how things move, how they break, and how to make them work again. Tony didn't just cool an engine. He rerouted the course of history, one piece of pipe at a time.